Hi. Okay, today we're going to talk about permeability and porosity. And remember, we talked about that with talking about soils. We talked about the fact that there were holes between the particles of the soil, and that the larger the particles were, the more likely water was to be able to drain through it. Draining through the soil is what we call permeability. Then we also talked about the fact that water would be trapped in those holes between the particles, and that the volume of those spaces was considered the porosity. So porosity has more to do with the ability of a soil to hold onto water, and permeability is regarding the ability of the water to flow through it. Now, we're on water, so why are we talking about soil again? Well, remember that an aquifer is an underground sponge for water. And that sponge is made up of particles of soil trapped between layers of clay or porous rock that trap the water in from going down too far. So the water filters through the recharge zone into the zone of aeration, and then finally down into the aquifer, which is actually a layer of soil, okay, that may be compacted to some degree above an impermeable layer of either clay, which is ultimately going to allow the water to flow through very, very slowly, or a layer of rock that may allow the water to flow through very slowly. But in the meantime, that water is going to stay in that aquifer between the zone of aeration and that impermeable layer. So we're going to take a look at this area right in here, taking a look at these three soil samples. Okay, so what we have here is we have some sand, and we have some clay, and we have some humus. So we're going to, let me switch those two around. Okay, so we're going to take a look at how each of these soil samples flows and holds water. Okay, so what I've done is I've taken a tube. This is a hollow tube at both ends. You have open end here, but at this open end I've put some gauze and a rubber band, and that is just simply to hold the soil in, but also to allow the water to flow through. So I've trimmed it all off here, and then I'm suspending it in this other container just using a couple of twist ties. So it's really simple. This kit comes from Carolina Biological or Fisher, any number of them that have a soil permeability, but you can improvise this with some things that you could probably buy at Target or Home Depot. So we're going to measure that. So then what we did was we measured off 7 centimeters from the bottom of the tube up to here. And then I filled each of the tubes with the same volume of soil. Okay, so each of these has the same volume of soil, 7 centimeters times the diameter of this tube. So each of them has the same volume of soil. They don't have the same mass of soil because each of the soils, of course, has their own mass. So what I've done is I've made myself a little chart here with the sand, the humus, and the clay, and I measured the dry weight of the sand of the soil sample plus the gauze, rubber band, and tube. Okay, and so for this one I got 25 for the sand, 10 for the humus, and 17 for the clay. But before I had filled the tubes, I measured the empty tube. So I know that the empty tube weighs 3 grams. So I'm going to subtract that empty weight from the dry weight to get the actual dry weight of the soil. And that's going to come in handy later when we're looking at the porosity. First thing we're going to do though is we're going to look at the permeability. Okay, so I need to get my stopwatch going here. So we're going to get our stopwatches going, and what is important is we're going to time how long it takes for the first drip of water to come through, and then time how long it takes for all the water to drain through. Okay, so first drip to last drip. That's what we're going to record. So we need to get both of those numbers down. So I'm going to have my board handy so I can write that down. All right, so I'm going to put the time, first drip, and time last drip on my chart here. Okay, and I'm going to start with the sand. And I'm going to fill the top of this tube from the top to the sand soil, and that should be about 10 milliliters of water. So I'm going to pour 10 milliliters of water into this graduated cylinder. so that I know for sure how much I poured in there, because I want to know how much I get back out again. So here's my 10 milliliters of water. Okay, so 10 milliliters of water. I'm going to pour it in. As soon as I start pouring, I'm going to press the start button. As soon as that water hits the sand, okay, there's 10 milliliters in there. Okay, I actually got a little less than 10 milliliters in there, so let's watch. It's going to work its way down through the sand. Okay, you can see it. It's kind of hard to see from way back there, but you can see now the water is about down to here on the sand. It's going to keep draining through, keep draining through. Okay, we'll do the same thing with each of these, find out what the first drop was and the last drop was. Now, can you, while you're watching, kind of make a prediction? Which of these do you think is going to have the fastest first drip? Is it going to be the sand, the humus, or the clay? Right, you keep that in mind. That's your hypothesis as to the first drip. Okay, which one is going to drip first? All right, now, while you're thinking about that, also think about which one do you think will hold the most water? Again, will the sand hold the most, the humus, or the clay? Okay, so those are your two hypotheses. Which one is going to have the greatest permeability, i.e., which one's going to allow the water to flow the fastest, and two, which one is going to hold the most water? Okay, so jot those down in your own little journal there, piece of paper that you're going to make your hypothesis. And it looks like we're almost ready to drip here. We're getting down there. And you notice that the water is draining off the top. Okay, I'm going to add the rest of my 10 milliliters in here because I want to make sure that I put all 10 milliliters in there. And my first drop is done. Okay, so 1 minute and 39 seconds to my first drop. Okay, so I'm going to let that keep dripping. And in the meantime, I'm going to pour 10 more milliliters into my graduated cylinder. Always have your graduated cylinder at eye level when you're trying to measure, and you're looking for the bottom of that little meniscus there. Okay, and so there's my 10 milliliters ready to go for that one. Unfortunately, I don't have more than one timer, so we're going to have to wait for this one to drip before I move on. If you do this experiment with your kids, you could have each of them doing a separate one and time it, or you could have several timers going at the same time. But it takes some observation. You have to have somebody watching this while you're doing it because you don't want to miss that first or last drip. Okay, oh, looks like we're almost done. The water's almost through. Now it's interesting because the water's flowed through, but I still have this little dry patch. See that little dry patch right there? So there's still part of this sand that is not saturated with water. All right, so everything has run through the top. Now I'm just waiting to see if it's going to keep dripping. Looks like that's my last drip. Okay, so last drip. Oh dear, we didn't start our timer. Pooey. Well, that's very different. Never mind. All right, well, let's try the next one. We'll try this again. We'll come back and do the soil again, the sand again for timing. We can still work on it for the amount of water that it left. So let's reset this timer, okay, and add our 10 milliliters of water to our humus. Ready with our stopwatch and start. Okay, pour that water. Oh, look, that already started dripping. 4 seconds. Okay, 4.3 seconds. 4.3 seconds to start dripping. And look at that. That got wet all the way through already. And almost ready for that last drop. Just give it a little tap. Okay, last drop. 23.7 seconds to the last drop. Wow, that was pretty fast. Okay, so this one has already drained out for us. Okay, so that was really fast. So that is 23 seconds, 23.7 to 4.3. We got a little less than 19 seconds, a little over 19 seconds for it to drip. But let's wait and see that water at the bottom. We're going to, again, check that for porosity in a little bit, okay? All right, last one, and this is our make sure we got all our water. Yeah, poured all our water in there. All right, so let's measure our 10 milliliters here. Okay, perfect. 10 milliliters. Okay, clear our timer. All right, and ready, set, go. Start that timer. Pour all the water in the top there. All right. So watching this one go down. And while we're watching this one, what I'm going to do is I'm going to go ahead and weigh these two tubes, the sand. Okay, so we're going to weigh that sand. Let's clear our scale off. I'm sorry, my scale can't be on the screen here. All right, so we weighed the wet sand, and the wet sand weighed 31 grams. Okay, so the wet sand, 31 grams. All right, and the wet humus weighed 16 grams. Okay, 16 grams for the wet humus. All right then. Now you can see our clay is taking a while, isn't it? We've been a minute already, and it's only a little ways down there, so it might take a little while for this to drain all the way through. So we're going to come back and I'll keep timing this, and I'm going to go reset this sand so we can measure the permeability again. Got some good porosity numbers, but we need a permeability because I messed up the first time. So I'm going to go ahead and reset this sand and wait for this clay to drip, because trust me, it's going to be a while. We'll be back. Okay, we're back, and it's been over an hour since our water was poured into our clay. It took 34 minutes and 9 seconds for our clay to finally drip. And now it has been over an hour since we left you, and we are still waiting for the last of our clay to drip. So here we go. So while we're waiting for the last of our clay to drip, and we'll get those numbers in there just a minute, let's go ahead and take a look at what happened with our sand and our humus. Okay, so here's our numbers. Now remember, I messed up on the sand and didn't turn my timer back on, so I kind of had to start over again. So I remeasured the dry weights. Okay, so now I have the weight of the dry soil for each of them, 20 grams here, 7 and 14. And I have the wet soil for the sand was 28 grams, for the humus was 16. And so when I subtract that out to get the weight of the water, okay, weight of the water is the difference between the dry soil and the wet soil, I get 8 grams for the sand and 9 grams for the humus. Now that's interesting, okay, because they're fairly close together, so that means that they both held on to a reasonably similar amount of water, okay? And sure enough, when I get down to the bottom here, you can see that when I measured the amount of water that came out, see the bottom water in the bottom of the test tubes, the humus gave me 5.1 milliliters, and the sand gave me 5.6. So that's how much water came out of those two. Okay, but look how much time it took. It's kind of interesting. The humus only took 19.4 seconds, and the sand took a little over 2 minutes, just a shy over 2 minutes for all the water to drain through. And like I said, it's been over an hour since we started the clay. It's now been an hour and 5 minutes for the clay. There was another drip. It's still dripping a little bit. There's another little drip coming. Okay, so, and look how much water we have in the bottom of that one. Okay, compared to what we have. Oh dear, don't pour the water on the computer, Miss Cooper. See, we got the water. Oh darn, we've just absorbed all that. All right, so see how much water we have in the bottom of that versus the bottom of this. So we have very little water coming out of the clay, but we had a fair amount of water come out of the sand. All right, so we don't even really have to wait for the clay to be done to declare some permeability here, do we? All right, so permeability is the ability to release water. Okay, so we can judge that on one of two things, time or amount. All right, so let's take a look at this. In terms of time, which one is the most permeable? Yeah, the humus is the most permeable based on time because it flowed through very quickly, 23.7. So that means that the spaces between the humus particles must be really big compared to the sand, right? So sand took 2 minutes, okay? So it took like what, 10 times longer, almost 10 times longer for it to move through the sand than the humus. So the humus particles, the individual particles of humus must be bigger and chunkier than the sand because they leave lots of really big spaces between them, where the sand spaces are much smaller. But what can we say about the clay? The clay has taken over an hour to drip all of that. So what can we say about the spaces between the clay? Yeah, they're teeny tiny. Very tiny little spaces, very tiny little spaces. And so this water is having to, it has to move back and forth, maybe even backwards a little bit to find its way down through all those little teeny tiny particles. But through the humus, the particles moved very rapidly. The water moved very rapidly through that. And then through the sand, it moved just a little bit more rapidly than the clay. Well, a lot more rapidly because, good grief, it's taken over an hour for it to go through the clay. Now let's take a look at how much water it let go. All right, so again, the humus let go 5.1 milliliters and the water let go 5.6. So in terms of the amount of water that came out, which one is more permeable? Yeah, the sand, because it actually released more water. Well, how is that? If the clay, if the humus has big chunky particles, why didn't it let go of more of the water? Well, because those particles themselves are absorbent. Okay, that's why we add humus to the soil. We add humus to our soil to make it absorb water. We want water to be absorbed into the soil so that it can hold on to the water and give it back to the plants. So that's one of the reasons that it does that. The sand, on the other hand, one thing that's very interesting about the sand and the other aspect of this in terms of permeability and porosity with respect to aquifers, which is why we're talking about this in terms of the water and not the soil, is because we need to see how much water can we get back out. Okay, so 8 grams here, 9 grams here, and this looks like it's pretty much done. There's no water on the top left. It doesn't look like it's going to drip again. So let's weigh this one real quick. See how much we had in there. All right, so that's 26. So let's add that to our list over here. So the wet weight was 26 grams, okay? And subtract the 14 grams from originally, and that means that the clay is holding on to 12 grams, okay? Additional 12 grams, okay? And as I said, it took over an hour, so that was about 1 hour, 10 minutes, and 32 seconds. So we're at, what is that, 60, 70 minus 70 minus 34, so we're at 34 seconds. So it took over an hour and 10 minutes for that to fully drain. Okay, from drop to drop, it took about 40 minutes. Okay, now let's see how much water it gave us back. All right, so we'll set that aside for just a second and pour that water into our graduated cylinder. And dun da da dun, we have 2.3 milliliters. 2.3 milliliters is what came back out of that. Okay, so 2.3 milliliters. Wow. So there's a big difference between how much was held by the sand, how much was released by the sand, and how much was released by the clay. Where is all the water? Where did it go? Yeah, it's in the particles. It's in the spaces between the clay particles. Okay? It's in between those clay particles. And yeah, it'll eventually drain out. We could leave this sucker hanging here for a couple of years and it'll eventually drain out or it'll evaporate out. But it's in between those particles. So when we talk about the aquifer, remember we have to have a recharge zone where the water will go through very quickly, okay, and not be held on to very much. We need another layer where it will drain into relatively quickly, but stay there. And then we need another layer where it's not going to drain through very quickly. And so the clay is what is down below it. And think about it if it's compacted clay. If you had compacted this down into this tube and then tried to pour water through it, you could be sitting here for days before it would do anything, maybe years. So the clay is that lowest level of our aquifer. Then we have to have a layer of the aquifer that is able to take in a lot of water, but also release it. Here's another little trick. Okay, let's take a look at this. Here's my sand. Okay, I'm going to put this pipette in my sand, and I'm going to suck up some water. Look at that. I was able to suck water out of the sand. Now I bet if I kept doing that, I could suck all of the water out of that sand. See? Water in the spaces between the particles. That's what we want for an aquifer. We want there to be spaces between the soil particles where the water can reside, but where it will stay and be able to be extracted. Because what good is water in an aquifer if we can't extract it, right? Now what about the humus? A lot of water went into the humus, a lot of water went through the humus, but can we suck the water back out? Not really. There's a tiny little bit of that. But that's good if that's the recharge zone, right? Because the recharge zone, we want the water to flow through quickly into our aquifer where it's going to be held onto. Can I get any out of the clay? Let's try that. Nope, all I get is clay. Okay, no water in there. Yeah, there's water in between those particles, but it's too hard to squeeze it out. So that's a good thing too, because we don't want the water that goes into the aquifer to flow out of the aquifer. So we need this clay layer below the aquifer itself to keep the water from flowing away. Now again, eventually this water is going to seep out. And if I squeeze my clay, I can squeeze some water out of there. But again, look how slowly it goes, all right? Can I squeeze the water out of my sand? Not as easily, but I can suck it out a lot easier. So that means that that water's not going to escape us underneath that pressure. Okay, how about my oh, there we go. See, but I can squeeze this guy. So if he gets compacted above, then I can squeeze some more water out of him. Okay, so when we talk about porosity and permeability, permeability is the ability to release water. And we have two measures, time and amount. Okay, so permeability can be measured in terms of the amount of time it takes for the water to flow through. It can also be measured by the amount of water that flows through that aquifer. Okay? Porosity, on the other hand, is how much water is held in the particles. Okay? So if we hold the water in the particles, then that is the porosity. So we know from the amount of water mass in the particles, oops, we erased our number. Okay? The amount of water, mass of water in the soil that clay has the greatest permeability. Okay, this one right here has our greatest permeability. Okay, and this has our least permeability, or porosity, excuse me. So porosity, clay has the greatest porosity, sand has the least porosity. When we look at our permeability, our humus and our sand had the greatest permeability, and our clay had the least permeability. Okay, so this one has high porosity, and this one has high permeability. Okay, so that's porosity and permeability and how that relates to aquifers. It also relates to how we use soils. So remember, when we went through the soil ID, the amount of clay and sand mixed in our soil made a soil better or worse for certain situations, right? So you want a mixture of sand and clay, and of course our silt, but in this case we're using humus. You want a mixture of those two things so that you can hold on to a certain amount of water, but release the water quickly enough that you're not drowning the roots of your plant. The other thing that clay brings to the picture in terms of soil is it brings the fact that because it has all of these minerals trapped in its particles, those minerals mix with the water that it's holding on to and comes out through the water and the sand. So minerals are added by clay. Clay has the ability to hold on to the water. Sand allows the minerals to disperse through the soil and allows the water to be absorbed by the plants. So very important to have the proper mixture of clay and sand in your soil. Now, most of the time when you go to ask the extension service about how to make your soil better, they're going to tell you to add one of these three things. They're going to say if you need nutrients, you need to add some clay. Okay? If you need water holding ability, okay, you need to add a little bit of clay. If you need water drainage, then you need to add a little bit of sand. And if you need a little bit of organic matter to help add nutrients and water holding capability, then you need to add your humus. So your humus is kind of in between the two of these. Okay? It works with the clay to add minerals and water holding. It works with the sand to allow water to drain, to lighten the soil so that it will drain better. So if you're working with your garden and you're trying to make it work better, have your soil analyzed for how much sand, silt, and clay there is, and then adjust your soil according to whether you need nutrients, whether you need water, or maybe you need a little bit of both. Okay? There's porosity and permeability, and yes, there's no write-up for this. This was just an informational. This is a little bit above and beyond what your elementary kids will need to know, but very important thing for adults to need to know, and also we want our kids to go into farming because somebody's got to grow the food, right? So if we understand that about our soil, but the other thing is this is extremely important. This porosity and permeability is extremely important to our aquifers. And if we remember that our aquifers contain 0.678% of the world's water, the more we understand about how our aquifers work, the better we can utilize them sustainably.